this video, I am going to explain about important synopsis of solid state, which is very important for competitive exams. So first, lesson structure. Here we'll discuss Bragg's equation, crystal lattice, unit cell, closed pack structures, tetrahedral voids and octahedral voids, packing efficiency or packing fraction, density of unit cell, defects, Scotty defect, Frenkel defect and interstitial defect, electrical properties, band theory and magnetic properties. We will discuss all these. So first one, classification of solids based on arrangement of constituent particles. So solids are classified into two types, which is crystalline and amorphous. So crystalline means having definite geometry. Crystalline means having definite geometry, and amorphous solids means having no definite form. So very important. So crystalline means definite geometry and amorphous no definite form. Here these are the properties. The first property, melting point. These are having sharp melting point. Crystalline solids are having sharp melting point. So for amorphous solids there will be no sharp melting point. So these are having range of melting point, range. Anisotropic, that means anisotropic. Crystalline solids are anisotropic. That means properties are different at different points or different at different directions. Next, isotropic. Amorphous solids are isotropic. That means properties are identical at all points. Next, nature. These are considered as true solids or perfect solids. So these are pseudo solids or supercooled liquids. Next, arrangement. So crystalline solids are having long range orders. Here these are having short range orders. So this is about classification of solids based on arrangement. Next, Bragg's equation will be having this equation n lambda equal to 2d sin theta. So where n is order of diffraction or refraction or deflection. Next, lambda, wavelength of incident X-rays, theta, angle of diffraction, d, interplanar distance, that means distance between two planes. So based on this we can calculate distance between two planes. Next, crystal lattice or space lattice. Space lattice. Crystal lattice or space lattice. So it is regular three-dimensional arrangement of points in space. It will be known as crystal lattice or space lattice. Next, crystal lattice does not indicate the structure of the crystal. So it represents only arrangement of particles in space. Next, so what is lattice point? Here lattice point can be either atom or molecule or ion. Lattice point means the constituent particle in crystal lattice. It may be atom or molecule or ion. So crystal lattice or space lattice is regular three-dimensional arrangement of lattice points in space. Next, unit cell. So it is the smallest repeating unit from which total crystal can be obtained is unit cell. That means properties of crystal lattice identical with the properties of unit cell. Properties of crystal lattice identical with the properties of unit cell. So unit cell is the smallest portion and crystal lattice is total arrangement of particles. Next. So types of unit cells. These are four types. Primitive cells. Primitive cells are simple cubic arrangement. So here particles will be only at corners. Particles will be only at corners. Next. The effective number of atoms can be calculated by taking contribution. So if atom is present at corner, it can contribute 1 by 8 to that cube. If atom is present at face center, it can contribute 1 by 2 to that cube. So if atom is present at edge center, it can contribute 1 by 4. Next, body center 1. These are positions and their contributions. If atom is present at a corner, contribution will be 1 by 8 to that cube. If atom is present at face center, 1 by 2. Edge center, 1 by 4. Body center, 1. So based on this, we can calculate effective number of atoms per unit cell. See here. Primitive cell, which contains lattice points only at corners, 8 corners. So corner contribution 1 by 8. Therefore 8 into 1 by 8, 1. So therefore 1 atom per unit cell, like this. 1 atom per unit cell. Next, similarly face centered cubic. So in case of face centered cubic, so atoms will be at 8 corners and 6 face centers. So 8 into 1 by 8 plus 6 into 1 by 2, therefore total 4. So 4 means here 4 atoms per unit cell. 4 atoms per unit cell. Next, similarly, body centered cubic. Body centered cubic. Atoms will be at 8 corners and 1 body center. Therefore, effective number of atoms 8 into 1 by 8 plus 1 into 1, 2. Therefore, 2 atoms per unit cell. Next, end face centered. End face centered. So, particles 8 corners and centers of any two opposite faces. That means 8 into 1 by 8 plus 2 into 1 by 2. Therefore, total 2. 2 atoms per unit cell. 2 atoms per unit cell. 2 atoms per unit cell. Remember this. Very, very important. Next. Closed pack structures in 2 dimension and 3 dimension. These are 2 dimension. Remaining are 3 dimensions. So, square closed packing. Square closed packing will be having coordination number of 4. Coordination number 4. Hexagonal closed packing coordination number 6. Simple cubic coordination number 6. HCP 3-dimensional 12. CCP or FCC 3-dimensional 12. Remember these coordination numbers in closed pack structures in 2 dimension, 3 dimension. Very, very important. Next. tetrahedral void and octahedral void. So for the formation of tetrahedral void, 4 atoms are required. 4 atoms. So I will write here tetrahedral void. Tetrahedral void. And here octahedral void. So here void means nothing but empty space. Empty space. So it is formed by placing 3 spheres in one layer. 3 spheres in one layer and fourth sphere above the 3 spheres in next layer like this. So this is tetrahedral void. So this gap will be tetrahedral void. So it is formed by 4 atoms. Next, octahedral void. 3 spheres in one layer. Next, 3 more spheres above the 3 spheres. I will write with different color. 3 more spheres in different layers. That means in second layer in opposite direction. So here void will be center space. This point will be octahedral void. So tetrahedral void shape will be like this. Tetrahedral void. Octahedral void like this. Octahedral void. Remember this. It is formed by 6 atoms. 3 atoms in one layer. 3 more atoms in next layer above the 3 atoms in opposite direction. So tetrahedral void will be formed by 4 atoms. Octahedral void 6 atoms. Next, if effective number of atoms in unit cell is n, effective number of atoms per unit cell equal to capital N, then there will be n octahedral voids and 2n tetrahedral voids. Remember this. Effective number of atoms n octahedral voids, 2n tetrahedral voids will be. Here it is given. A tetrahedral void is formed when 4 spheres are joined. 4 spheres are joined. Next, if the number of closed packed spheres, that means effective number of atoms n, then tetrahedral voids 2n. Octahedral void is formed when centers of 6 spheres are joined when 2 layers are arranged in hexagonal closed packing. Next, if effective number of atoms n, then octahedral voids also n. Same number of octahedral voids. Next, packing efficiency or packing fraction. So packing efficiency is volume occupied by atoms by total volume of unit cell. Here it should be unit cell. Unit cell. Total volume of unit cell into 100. So in case of BCC, body centered cubic, packing efficiency 68%. Remember these values. Packing efficiency in simple cubic or primitive cell 52.4. Next, packing efficiency in HCP or CCP 74. HCP means hexagonal close packing, CCP cubic close packing. Next, so void space can be calculated by using 100 minus packing efficiency. So void space means empty space. Empty space equal 100 minus packing efficiency. Very, very important. Next, density of unit cell D Z into M by A cube into Na or N naught. Avogadro's number. Z is density. Z is effective number of atoms in unit cell. D is density. So D is density in grams per centimeter cube generally, or kg per meter cube. In any way you can calculate. So D is density, Z is effective number of atoms per unit cell, M molar mass or atomic mass. If it is atom, we can take atomic mass. A volume of unit cell, and A is edge length, A cube is volume. Edge length. And A cube is volume. Next, Na, Avogadro's number. Avogadro's number we know 6.022 into 10 power 23, which is constant. So based on this, we can calculate density. So here this is packing efficiency and density. Next, defects. Defect means deviation from ideal behavior. Defect, deviation from ideal arrangement. Ideal arrangement of atoms. That will be defect. So here Scotty defect and Frankel defect are stoichiometric defects. Schottky. Scotty and Frankel defects. Stoichiometric defects. Very, very important. Stoichiometric means formula will not be changed. So Scotty defect is due to missing of equal number of cations and anions from their lattice positions. Missing of equal number of cations and anions from their lattice positions. Next, this is possible in ionic compounds with high coordination number. Here what is coordination number? Number of nearest atoms or number of nearest ions that are surrounding a particular ion. So number of oppositely charged ions that are surrounding a particular ion in ionic crystal. Very, very important. Next, So in Scotty defect, due to missing, the density decreases. Density of unit cell decreases or crystal decreases. So these are the examples. Next, Frenkel defect. It is due to dislocation of cation from original position and occupies interstitial site. Interstitial site means gap between ions. So Scotty defect is also known as vacancy defect. It is also known as vacancy. Complete missing. Vacancy defect. And Frenkel defect is interstitial defect. Or dislocation defect. You can say dislocation. Scotty defect is due to complete missing of cations and anions. Therefore, vacancies will be formed. So, in Frenkel defect, cation occupies interstitial position. Next, it is most common in ionic compounds with low coordination number. So, a density remains same. These are the examples. So, here AZBR can exhibit two types of defects. Scotty defect as well as Frenkel defect. That is previous question, very very important. Next, interstitial defect. So this defect arises when some constituent particles are missing from their original lattice and occupy interstitial sites of crystal. Interstitial positions means gaps between metal atoms or gaps between ions. So these are ions and this position will be interstitial. Position. Gaps between constituent particles, interstitial positions. And these are lattice points. Lattice points. So very very important. Next, F centers or color centers. F centers are also known as color center. So these are possible in metal excess defect. Metal excess defect due to anion vacancy. Anion is missing from its lattice position and vacant sites are occupied by electrons. These electrons are known as F centers because these are giving, that means these are responsible for color of the crystal. And due to the presence of unpaired electrons, it is paramagnetic in nature, metal excess defect. So very very important. So due to F centers, that means metal excess defect, NaCl color will be yellow. KCl color will be lilac or violet. And LiCl color will be pink due to F centers. So LCl minus ion will be missing from its lattice position and these positions are occupied by corresponding number of electrons. These electrons are responsible for color. Next, electrical properties. Semiconductors first. Semiconductors means conductance lies between conductors and insulators. So these are two types, N type and P type of semiconductors. Next, Semiconductors are obtained by addition of small amount of either fifth A group into pure silicon or germanium or N type of semiconductors. The semiconductors which are obtained by addition of small amount of fifth A group element, phosphorus or arsenic, into pure silicon or germanium is N type. So N type will be obtained by addition of, so N means negative, remember, addition of fifth A group element. Next, P type will be formed by addition of, P type means here positive hole. It is formed by addition of third A. Third A group element to silicon or germanium. Here also to silicon or germanium. So this process will be known as doping. Doping. See why it is N type means, see 4 out of 5 electrons of phosphorus or arsenic will be used for bonding, while fifth electron involved in electrical conductance. One electron is excess. So 4 electrons will be used in bonding and 1 electron will be free. So this involves in electrical conductance. Therefore, negative. Excess electron is present. Due to the excess of electron, this becomes negative type. Next, P type. The semiconductors are obtained by addition of third A group elements, boron, aluminum, gallium, indium, into pure silicon or germanium. Next, 3 electrons of boron or aluminum are used for bonding, while fourth is the hole, which is responsible for conductance. So, in fourth valency is vacant. Therefore, that is known as hole, positive hole. So, in case of N type, excess electron is responsible for conductance. In case of P type, positive hole is responsible for conductance. Next. So, band theory. So, here conductors, semiconductors and insulators. See, first conductors. These solids with conductivities ranging from 10 power 4 to 10 power 7 are conductors, high value, very high value. Next, here semiconductors, conductivity in between 10 power minus 6 to 10 power 4. Next, in case of conductors, gap between filled valence band and the conduction band is very small. That means simply like this. You will write here. Conductors, semiconductors, and insulators. So here two types of bands will be there. So gaps will be like this. So this is conduction band. In case of conductors, both are mixing. Negligible gap. That means almost no gap. So this is valence band. Valence band, and this one conduction band. Therefore, these are best conductors. So very, very important. In case of semiconductors, semiconductors, valence band and conduction band. Gap is small, very small. Here gap is small. Next, insulators. Like this it will be. So very, very important, this difference. Valence band and the conduction band. Very large gap. Check here these three. Now see the points. See in case of conductors, so very small. The gap between valence band and the conduction band is very, very small. Therefore, they can conduct electricity easily. Next, semiconductors, see here. Gap between valence band and the conduction band is small. While in case of insulators, see, gap between valence band and conduction band is very large. Next, check these points once again. Next. So here conductance is due to movement of electrons or ions. Next. Next, semiconductors. These are the conductors in which conductance lies between 10 power minus 6 to 10 power 4. Conductors 10 power plus 4 to 10 power plus 7. Easy to remember. In case of conductors, both are plus values, 10 power plus 4, 10 power plus 7. In case of semiconductors, one minus value, one plus value, 10 power. Next, electrical conductivity of semiconductors increases with increase of temperature due to the movement of free electrons or positive hole. Next, insulators. So conductance values are very low. Both are minus values here. 10 power minus 20, 10 power minus 10. Easy to remember. So here Ohm inverse must be there. OH. Ohm inverse, metal inverse. Next, gap is very large. Check the difference. Conductors, very small gap. Semiconductors, small gap. And in case of insulators, very large gap between valence band and conduction band. Next, magnetic properties. So ferromagnetism, here magnetic properties are 5 types. First one, ferromagnetism. Next, paramagnetism. Next, diamagnetism, antiferro, antiferromagnetism, and at last ferrimagnetism. These are 5 types. So ferromagnetism is due to this electronic arrangement, ferromagnetism. All electrons will be aligned in same direction. Paramagnetism, this is also due to unpaired electrons but zigzag movement. Unpaired electrons but in zigzag movement. Diamagnetism, pairing of electrons like this. Pairing of electrons in same orbital like this. Antiferro, equal number of upward and downward arrows. That means electrons arrangement. One upward, one downward. One upward, one downward, like that. Ferrimagnetism, unequal number of upward and downward. This is electronic arrangement in case of different magnetic materials. So ferromagnetic materials means strongly attracted by external magnetic field. So iron, cobalt, nickel, best examples. One more, CrO2 is there. CrO2 also ferromagnetic material. Next, paramagnetism is due to unpaired electrons and these are weakly attracted by external magnetic field. So generally transition metal ions. Transition metal ions. Next, ferrimagnetism. Ferrimagnetism, here ferrimagnetism, unequal number of upward and downward arrows. Unequal number of upward and downward arrows. So these are also weakly attracted by external magnetic field. Examples, very very important. So here one divalent, one trivalent metal will be there. Next, antiferromagnetism. So here electron domains are arranged with equal number of upward and downward domains, downward electrons, equal number of upward and downward. So net dipole moment will be equal to 0. Remember these 5. Ferromagnetism, strongly attracted by external magnetic field. Para, weakly attracted. Diamagnetic means repelled, repelled by external magnetic field. Ferrimagnetism, unequal number of upward and downward. Antiferromagnetism, equal number of upward and downward. So here examples are very very important. 4 types. So this is the end of the synopsis. In next video I will explain model questions of solid state. All the best and thank you.